In this video, we're going to go over some practice problems on the material covered this week. So we're going to start with section 4.5 here. And in this section, we are just multiplying polynomials. So we're going to start with this question here. We want to find the product of this monomial multiplied with this trinomial here. So what's happening here is that this 5r cubed term is going to be distributed to every single term inside of our trinomial, or inside of the parentheses here. So it'll apply to every single term of this trinomial. So what's happening is we're going to have 5r cubed times 2r squared plus 5r cubed times 3r plus 5r cubed times 4. So in this case, we know from last week that when we're multiplying these terms like this here, what we're going to do is multiply the coefficients. So we can multiply 5 and 2, and then when we go ahead and multiply our variables here, so for example, this r cubed and this r squared, what happens is we're going to add the exponent powers. So here, this will give us 5 times 2, which is 10, and then r to the 3 plus 2 power, so r to the 5th power. So for the second term here, this is going to be 5 times 3, so that'll give us 15. And then r to the 3 plus 1, so r to the 4th power. And then lastly, we have 5r cubed times 4, so we're just going to multiply the 5 and the 4, so this will give us 20, and this r cubed term is going to stay there. So this would be our final answer when we're multiplying these two. Now for this question here, we have this m term, and then we have two binomials here, and we're multiplying all three of these guys. So the first thing that we'll do in this case is we're going to distribute this m on the outside to both terms inside of our parentheses here, similarly to what we did for the last example. So doing this, we're going to get m squared plus 5m, so just distributing that m to both terms inside our parentheses. And this is still being multiplied by this other binomial here. Now from here, what's happening is that both terms inside of our first binomial here are being multiplied to this guy. So this m squared is going to be multiplied to this guy, and so is this 5m. So we can rewrite this as m squared times our binomial plus 5m times our binomial. So this is one way that we can multiply these two, and we'll actually see another method in the next example. So from here, what we can do is distribute this m squared to both terms inside of our parentheses here, and we'll do the same thing for this 5m, distribute that to both terms inside of our parentheses. Doing this, we know when we multiply this m squared and this m, we're just going to add these exponents. So this will give us an m cubed and a minus 8m squared, then a plus 5m squared, and then a minus 40m here. Now from here we can combine like terms. These guys are like terms. So this will give us, we have this m cubed and then minus 3m squared minus 40m. So this would be our final answer here. So in this question 19 here, what we're doing is we're multiplying two binomials, and we saw that we can do that by multiplying the second binomial here by both terms in our first binomial. So that's what we have here. Now this is one way we could do this product. Another way is using the FOIL method. So this is going to stand for first, outer, inner, and last, and that's going to be the order in which we are going to multiply the terms in, for example, this product here. So the first terms in this first binomial is going to be 3x, and the first term in the second is going to be 2x. So these guys are going to be multiplied, and we're going to illustrate that with an arrow. Then we want to multiply our outer terms, so that'll be 3x and 3y, our inner terms, and our last terms. So doing this, we're going to get, we have 3x times 2x. That's going to be our first product here. Then we're going to add our second product, which is 3x times 3y, our third product, which is 4y times 2x, and then our last product, which would be 4y times 3y. Now let's simplify this here. We know that this is going to be 6x squared, this first term. Our second term is going to be 9xy. We can multiply these constants 3 here, but we can't multiply our x and y, so we're just left with an xy term here. Similarly, for our third term, we're going to multiply our 4 and 2, so we're going to get 8, and then xy. Let's fix that. And then lastly, we have 4y times 3y, so this will be 12y squared. From here, we can combine like terms. These guys are going to be like terms here. So we're going to have 6x squared. We have 9xy's, and we're going to add 8 more. This will give us 17xy's, and then we still have this 12y squared here. And so this will be our final answer here. We can't combine like terms any further. So that's how we would use the FOIL method. And this actually is a preferred method when multiplying two binomials rather than this method, but you can use whichever one you're more comfortable with. Alright, so let's look at this next question here. So we want to multiply these two binomials, so we're going to use our FOIL method that we saw in the last example. So we're going to multiply these guys, these, and these. And now this example is actually a special case, and we'll see why in a moment. So here our first terms are going to be 3x times 3x, so this is going to be 9x squared. We're going to add our second term, so that's going to be 3x times 8, so that would be 24x. Now our third term here is going to be this minus 8 times this 3x, so that would be minus 24x. And then lastly, we're going to multiply our outside terms, or our last terms, I mean. So this would be minus 8 times 8. So this would give us a minus 64 here. So now we can combine like terms. We have a positive 24x and a minus 24x. So that's why this is a special case here, because these guys are actually going to cancel out. And we're going to be left with just 9x squared minus 64. Now for this next question, we have to be a little careful. We have 2p plus 7 squared. So remember what it means to square something. For example, if we have x squared, this will be x times x. So if we have a plus b squared, for example, we're not going to distribute the square to both terms inside of our parentheses. What's happening is that this whole thing here is being squared. So this would be a plus b times a plus b. So in this example here, this would be 2p plus 7 times 2p plus 7. So from here, we can use our FOIL method. So these guys are going to be multiplied. This will give us, our first term is going to be 2p times 2p. So this will be 4p squared. Our second term is 2p times 7. So this will be plus 14p. And our third term is again going to be 2p times 7. So we have another 14p. And then our last term is going to be 7 times 7, so this will give us 49. So just combining like terms here, these guys are like terms. So we're going to have 4p squared plus 28p plus 49 is going to be our final answer here. Alright, so in these next two examples here, we're given three functions, f of x, g of x, and h of x. And first, we want to find this here. So this is going to be the product of these two polynomial functions, f of x and g of x, evaluated at x is equal to 2. Another way to write this would be f of 2 times g of 2. So our polynomial function, f of x evaluated at x is equal to 2 times g of x evaluated at x is equal to 2. So what we can do is evaluate these two functions at x is equal to 2 separately, and then multiply those values. So f of 2 we're going to find by plugging 2 into our x. This will give us minus 5. And then g of 2, we're going to do the same thing, just plug 2 in for x. So this will give us 4. So from here, f of 2 times g of 2 is going to be negative 5 times 4, which is going to give us negative 20 here. So this is one way that we can determine this value here by first finding these function values and then multiplying them. Or another way that we can determine this is to first multiply our two polynomial functions. So f of x times g of x, this would be x squared minus 9 times 2x. Now to multiply this, we're going to multiply x squared times 2x and minus 9 times 2x. So x squared times 2x, this will give us 2x cubed, and then minus 18x. Now from here, we want to figure out the product of these two polynomial functions, so this guy, evaluated at x is equal to 2. So what we can do is just plug in our value for x. Doing so, we're going to get 2 times 2 cubed. 2 cubed is 8, so multiplying that by 2, this will give us 16. And then 18 times 2 will give us 36. So 16 minus 36 gives us minus 20, and we end up with the same answer that we got in the first place here. So you can use either method. This one is a little bit easier, but whichever one you are more comfortable with using. All right, so for this last question here, we want to evaluate the product of these two polynomial functions at x is equal to minus 1. And so we're going to do this by first evaluating our two polynomial functions at this x value and then multiplying those two values. So f of negative 1 we can find by plugging negative 1 into f of x. Doing that here, we're going to get minus 8. Now we're going to do the same thing. We're going to plug negative 1 into h of x. This will give us negative 1 minus 3, which is negative 4. And then lastly, what we'll do is multiply these values to answer our original question. So we'll have negative 8 times negative 4, which gives us a positive 32. And this would be our final answer here. And again, we could also do it this way, how we did in this last example here, and you should get the same answer. So in section 4.5, we looked at multiplying polynomials. So now in section 4.6, we're going to look at dividing polynomials. And we're going to start with the simplest case here, and that's when we're dividing a polynomial by a monomial. So what happens in this case is that this term here, this monomial in our denominator, is going to divide every single term in our numerator. So we have 15m cubed is going to be divided by 5m cubed. Then 25m squared is going to be divided by 5m cubed as well. And lastly, 30m is divided by 5m cubed. So from here, we just want to simplify. We know that 15 divided by 5 is going to give us 3. And we have m cubed on the numerator and m cubed on the denominator of this fraction, so these guys are going to cancel. Now for our next term here, we have 25m squared divided by 5m cubed. Again, we're going to divide these coefficients here. So 25 divided by 5, that gives us 5. And then m squared divided by m cubed, what we can do is subtract these exponents like what we saw in the last section. Doing so, we're going to have 5 over m. Okay? We're going to have m to the power 2 minus 3, which is m to the power minus 1, and writing this with positive exponents gives us m in the denominator. All right, we could also think of this in terms of canceling, like how we saw in this case. We have 2 on the top and 3 on the bottom, so we're going to be left with 1 on the bottom. And then lastly here, we have 30m divided by 5m cubed. So 30 divided by 5 is going to give us 6. And again, we have m on the top, but m cubed on the bottom. So we're going to have m squared left over in the denominator of this guy. So this will be our final answer in this case. Now in this next example here is where it gets a little more complicated. We're dividing a trinomial by a binomial. So in this case, we can't split up each of these terms like how we saw in the last example. So there is a detailed procedure on how to do this in the textbook. So I definitely recommend going ahead and reviewing that if you haven't done so already. But what we're going to do here is we have this 2k squared minus 3k minus 20, and we're going to divide this by 2k plus 5. And so we're writing this in long division format here. This will help us kind of lay out each step. So the first step that we're always going to do is we're going to divide the first term in our numerator by the first term in our denominator here, this 2k. So step 1, we're going to have 2k squared divided by 2k. This gives us k. Now this result here is always going to be the first term in our result, and we're going to write our result above this bar here. Now the second step is going to be to multiply this result by what's in our denominator. Another term for this is our divisor. This is what we're dividing by. So we're going to multiply that result by our divisor. This will give us 2k squared plus 5k. Now next, this result here, what we're going to do is subtract it from our original polynomial. So we're going to subtract out 2k squared plus 5k. So when we subtract out this polynomial, remember this minus is going to be distributed to both terms inside of our parentheses here. So we're going to have a minus 2k squared minus 5k. So this 2k squared up here and this minus 2k squared, they're going to cancel. And then we have minus 3k minus 5k, so this will give us a minus 8k. So next what we want to do is bring down this remaining term here, so this will be minus 20. And so from here what we're going to do is essentially repeat this process. Our next step, I'm going to do it in different colors, step 3, is we're going to divide the first term in this result by the first term in our divisor. So we have minus 8k divided by 2k. This is going to give us a minus 4. And from this division here, this will give us our second term in our result. So that'll be minus 4. Now from here, we're again going to multiply this result by our divisor. Our divisor is 2k plus 5, and we're going to multiply that by minus 4. Doing so, this is going to give us a minus 8k minus 20. And then again, what we want to do is subtract out this result from this guy here. So we're going to subtract out minus 8k minus 20. Now notice, again, this minus is going to be distributed to both terms inside of our parentheses here. So we end up with a positive 8k and a positive 20. So this minus 8k and this positive 8k cancel, and this minus 20 and plus 20 also cancel. So what we're left with is 0, and in this case, this is going to be our remainder. So when we divide these two polynomials, we're left with a remainder 0. So this means our final answer is just going to be what's up top here, this k minus 4. Now in some instances, we might not be left with a remainder of 0, and we'll see that in a few examples. Now in this next example, we're looking at a special case here. So remember, polynomials are written in descending powers of the variable. So for this question, our variable is p, and as we can see, it's written that way. We have p cubed and then our p squared term, but notice we're missing our p term. So what we're going to do is we're going to add a term with a 0 coefficient, kind of like a placeholder for this missing p term. So what I mean is we're going to rewrite this polynomial in the numerator as p cubed plus 3p squared plus a 0p term minus 4. So this 0p here is just going to be a placeholder, and we're going to need that to divide these guys. So we're going to set this up like usual here. We're dividing this polynomial by p plus 2. So again, our first step is going to be to divide out the first terms. So p cubed divided by p. This will give us a p squared, and this is what's going to go up here. Now our second step, we're going to multiply this result p squared by our divisor, this p plus 2. Doing so, we're going to get p cubed plus 2p squared. And then with this, we're going to subtract out this result here from this guy. So subtracting out p cubed plus 2p squared. So this minus sign here is going to be distributed to both terms inside of our parentheses. So we're going to have p cubed minus p cubed. So these guys will cancel here. Then we have 3p squared minus 2p squared. So this will give us p squared here. And then we're going to bring down our two remaining terms. We have plus 0p minus 4. So from here, we're just going to repeat those same steps for step 3 here. What we're going to do is divide our p squared by p here. So we're going to get p squared over p, which is just going to give us p. Now this result is going to go up top here. All right, so for our next step here, we then want to multiply that result p by our divisor. So we have p plus 2 times p. So this will give us p squared plus 2p. And then we're going to repeat this process. So we're going to subtract out this result, this p squared plus 2p. Again, that minus sign is going to be distributed to both terms inside of our parentheses. So we're going to have p squared minus p squared. So these guys are going to cancel. And then we're going to have 0p minus 2p. So this will give us just a minus 2p here. And then we're going to bring down our last term here, this minus 4. And then we're going to repeat those same steps again. So what we're going to do, let's keep color coding this, is we're going to divide minus 2p by this first term p here. So we have minus 2p divided by p. So this will give us a minus 2. And again, that's going to be our result up here. And again, we're going to multiply this result by our divisor. So this will be step 6 here. We're going to multiply our result minus 2 times p plus 2. So this will give us a minus 2p minus 4. And then again, we're going to subtract out that result here. So minus a minus 2p minus 4. All right, so subtracting these guys out, again, this minus sign is going to be distributed to both terms inside of our parentheses here. So we're going to get a minus 2p plus 2p, so these guys cancel. And then we have a minus 4 plus 4, so these guys will also cancel, and we're left with 0. So in this case, we see that we have a remainder of 0, and so our final answer is going to be this polynomial here. So dividing these two guys, we're going to get p squared plus p minus 2. Now in this next example here, we're also missing a term, but this time the term is missing from our numerator. We have k squared, but we're missing a k term. So we're going to follow the same procedure here. So we're dividing these guys. And what we're going to do is put a placeholder for this k term here. So we're dividing by k squared plus 0k minus 9. So in this case, this is our placeholder term. All right, so now we're going to move forward with the same steps that we've seen in the last several examples. We're first going to divide this term by this term here. So the leading term in both polynomials. So we have 3k cubed divided by k squared. This will give us a 3k, and this result's going to go up here. So for our next step, we're going to multiply this result, 3k, by our divisor here. Doing so, we're going to get 3k cubed minus 27k. And then again, we want to subtract out this result here. And so I'm actually going to again put a placeholder here for this k squared term. Notice this guy doesn't have a k squared term, so just so it's easy to see what we're doing here. So I'm going to add a placeholder for this guy, and then we still have this minus 27k. Now the reason being, we know when we subtract these guys, these are going to cancel. We have 3k cubed and then minus 3k cubed. Then here we have a k squared and a minus 0k squared. So this k-squared is just going to come down here. Then we have a 4k plus 27k, so this is going to give us a plus 31k. And then lastly, we're going to bring down this last term here, minus 5. So again, just putting this placeholder here so we can easily see that we are subtracting these polynomials vertically. So we're subtracting their like terms in this way here. All right, so we're going to repeat this process. We're going to divide this leading term here for this polynomial by the leading term in this polynomial. So for step 3 here, we're going to have k squared divided by a k squared. So this will give us 1. And then this result is going to go up here. And then for our 4th step here, we know we're going to multiply that result by our divisor. So this will just give us our divisor back. So we're going to subtract that guy out. Doing so here, our k-squared terms are going to cancel, but we're going to be left with 31k plus 4. So in this case, we're going to stop here, and this is going to be our remainder. Now, the reason that we know to stop here and that this is our remainder is because the degree of this resulting polynomial is less than the degree of our divisor. So whenever this happens, we can't divide evenly anymore. If we were to repeat this process here, we would divide this leading term by this leading term here, and that would result in negative exponents and fractional expressions, which we don't want. We can kind of relate this to regular numerical long division when we are using the same notation here and just dividing numbers. When the remainder here is less than the number we're dividing by, we can no longer divide evenly. So the same logic is applied here. And so for our final answer, what we'll write is this resulting polynomial here, this 3k plus 1, and then we're going to add our remainder over our divisor. So 31k plus 4 over our divisor, k squared minus 9. So this is the notation here whenever we end up with a divisor. So it'll always be our quotient, so what we got when dividing this, plus our remainder over our divisor. So whenever we're doing this polynomial long division here, our answer, which is called our quotient, or our result, plus our remainder over our divisor. So that's how we'd formally write our answers. And then notice if we don't have a remainder, so our remainder is 0, it would be our quotient or our result plus 0 or over our divisor, which is just 0. So that's why in these examples here, we didn't have to write our answer that way because there was no remainder. All right, so this brings us to our last question in this section. Given the pair of functions below, we want to find this here. Now this is some new notation. What this means is we want to take our polynomial function f of x and divide it by our other polynomial function g of x. So we're going to divide this polynomial by this guy. So our dividend, or our original polynomial, is going to be f of x, which is 2x squared minus x minus 3, and we're going to divide by x plus 1. So x plus 1 is our divisor. So we're just going to repeat the steps that we've seen in the last several examples. Our first step is to divide the leading term in our dividend by the leading term in our divisor. So this will give us 2x, and that result will go up here. For our next step, we're going to multiply that result by our divisor. This will give us 2x squared plus 2x, and so we're going to subtract out that result here. Doing so, we have 2x squared minus 2x squared, so these guys are going to cancel here. Then we have minus x minus 2x, so this will give us a minus 3x, and then we want to bring down this last term here, this minus 3. So we're going to repeat this process here. We're going to divide the leading term here by the leading term in this guy. So minus 3x divided by x gives us a minus 3. So that result will go up here. And then we're going to multiply that result by our divisor. Doing so, this will give us a minus 3x minus 3, and that's what we're going to subtract out from this guy. Doing so, this minus sign here is going to be distributed to both terms inside of our parentheses. So we're going to get minus 3x plus 3x. So these guys will cancel. And similarly, we have a minus 3 plus 3. So these guys will also cancel, and we're going to get a remainder of 0. So that means in this case, by dividing these two guys, our final answer is going to be 2x minus 3. Alright, so in these next two sections, 5.1 and 5.2, we're going to deal with factoring these polynomials. And we're going to start with factoring out the greatest common factor. So looking at question 19 here, we want to factor out the greatest common factor in this polynomial here. Now what that means is we want to figure out the greatest factor that these guys have in common, these two terms here. Now notice if we just look at their variables, we have a k cubed here, and then we have a k and a p here. So that means both of these guys share at least one k factor. So we know that we can factor it out or pull it out from both terms. Additionally, we have an 8 as this coefficient here, and if we were to take an 8 out of 24, so divide 24 by 8, we'd be left with a 3. So 8 is a factor of 24, and 8 is also a factor of 8. So with that, that means we can pull out a factor of 8k from both of these terms. So doing that, we're going to be left with 8k out in front, and then our first term, we're going to have a k squared, and for our second term, we're going to be left with 3p. Now, whenever we're factoring out a greatest common factor, we can always check our work because these guys should be exactly equal. So what I mean is when we distribute this 8k back into both of these terms, we should end up with our original polynomial. And we'll see that that is the case. 8k times k squared will give us 8k cubed, which is our first term, and then 8k times 3p, well 8 times 3 gives us 24, and then k times p gives us kp. So we know when we factor out the greatest common factor for this guy, this is what we get here. Now, moving on to question 27 here, we want to do the same thing. We want to pull out the greatest factor that they have in common, that these three terms now have in common. So first, notice these guys each have a factor of 5 in common, 15, 25, and 5. So we're going to at least pull out a 5 from all three of these terms. Next, we see that each of them has at least one factor of a. So we know we're going to pull out an a from these guys. And then lastly, they each have at least one factor of c. So we can pull out a c from all three of these guys. Doing so, what we're left with our first term here, we're pulling out a 5ac. We're going to be left with a 3ac squared. For our second term, pulling out a 5ac from this guy, we're going to be left with a minus 5c. And then lastly, if we pull out all of this guy, so 5ac from this guy, we're just going to be left with 1. We can always check our work by distributing this back into all three terms. If we were to multiply these two guys here, we're going to get 15, a squared, and c cubed. So that works for the first guy. For the second guy here, if we were to distribute this, we would get a minus 25ac squared. And then lastly, 5ac times 1 gives us 5ac. So we know that when we pull out the greatest common factor, we're left with that there. Now for this next example, we again want to pull out the greatest common factor for both of these terms. Now notice in this first term here, we have a 2 minus x squared, and then we have a 2 minus x cubed. So that means for both of these terms here, we have at least two factors of this 2 minus x here. So let's pull two of those guys out. So we have 2 minus x squared that we're pulling out. What we're left with, our first term, is just going to be 5 because we're pulling out this whole thing. And then our second term here, we're going to have 2, and then we still have 2 minus x left over. So from here, we can actually simplify this a little bit. We have this 2 minus x squared on the outside. On the inside, we can distribute this minus 2 to both terms in our parentheses here. So this will give us a 5 minus 4 plus 2x. And then lastly, we can simplify this one step further. We have 5 minus 4, which would give us 1. So we can write this as 2x. We can write this as, pencil is not responding. Okay, let's try this again. Okay, we can write this as 2x, and then 5 minus 4 is plus 1. So this would be our final simplified answer when we pull out the greatest common factor from these two terms here. Now for this next example, we want to factor this polynomial using a common factor with a negative coefficient. So we're going to pull out a greatest common factor, but that greatest common factor needs to have a negative coefficient. So if you can see it right away, you can just go ahead and pull that out. But if you can't, an easy way to see what's going on is to do this in 2 steps. Since we know we want to have a negative coefficient, the first thing that we can do is just pull out a negative from each of these terms here. Doing so, we're going to be left with all of these terms here are going to have different signs. So we're going to have a positive r cubed, a minus 3r squared, a minus 5r. Now from here, we want to pull out the greatest common factor. We'll notice that each of these guys shares a factor of r. So if we pull that out, we're going to be left with a minus r on the outside, r squared minus 3r minus 5 on the inside. And so this is how we would factor this, by pulling out the greatest common factor with a negative coefficient here. Now again, if you can look at this and automatically see that you need to pull out a minus r, you can go ahead and do that in one step, but I'm just showing and emphasizing what it would look like if we pulled out a minus from each of these guys here. Now for the next several examples, we're going to be factoring by grouping. So we'll use this factoring method usually when a polynomial has more than 3 terms. And we'll see that this is the case when the individual terms of a polynomial are going to have greatest common factor of 1. So for this question 51 here, we want to factor this guy by grouping. And the first step is to essentially group the terms in pairs so that each pair has a common factor. So for example, let's group these guys so that we have mx and qx as one pair, and then my and qy as our second pair. Now notice this pair shares a common factor of x, and this pair shares a common factor of y, so we know that we've grouped these guys appropriately. So from here, what we want to do is pull out that common factor. So we're left with this as our first term, and then for our second term, pulling out the common factor of y, we're left with this here. Now notice both of these terms share a common factor of this m plus q here. So what we can do is just pull that guy out. Doing so, for our first term, we're just going to be left with an x, and for our second term, we're just going to be left with a y. So we're going to get x plus y here, and this is our fully factored form. Now, something else that I wanted to point out for this example is that we actually could have grouped these guys a little differently. We could have grouped the first pair as mx plus my, and then the second qx plus qy. Now the reason being is because we still have grouped these guys appropriately. This is because our first pair shares a common factor of m and our second a common factor of q. So we can follow the same steps and pull out these common factors. We're left with this here. Now notice these two terms share a common factor of x plus y, so we can pull that guy out. Doing so, our first term, we're just going to be left with an m, and for our second, we're going to be left with a q. So we have m plus q here, and notice this is exactly what we got when we did it this first way here. So it doesn't necessarily matter in which way you group these guys as long as you group them in pairs that share a common factor. So for this next example, I'm going to group them like this here. We have p squared plus pq. This will be my first pair. And my second pair will be minus 4zq minus 4pz. So for this first pair, they share a factor of p, and for the second, they share a factor of minus 4 z. So I'm going to pull out those common factors from each pair. I'm left with p on the outside of p plus q for the first term. Now for the second term, I'm going to pull out a minus 4z. So we'll have minus 4z out front. And then we're left with, since I pulled out this minus here, we have a negative coefficient. It's going to change the signs of these guys. So I'm just going to be left with a q and then a plus p, since we pulled out this minus. So this will be q plus p. And notice p plus q is the same as q plus p, so we can pull that guy out. So we have p plus q, and what we're left with our first term is p, and our second term is minus 4z. So this would be our answer for this one when we factor by grouping. There we go. So for this next example, I'm going to group the terms exactly like how they're written here. So this will be my first pair, and then this will be my second pair. So for my first pair, they share a common factor of 4m squared. And what I'm going to do is also pull out a minus 4m squared. So pulling this out, I'm going to be left with a positive 4m and then a minus p squared. So we have 4m minus p squared. Now for my next pair here, they share a common factor of p, so I'm going to pull out a minus p. Doing that, I'm going to be left with a positive 4m for my first term, and then a minus p squared for my second. Now notice we have two terms now, and they share a common factor of 4m minus p squared. So pulling that out, I'm going to be left with, my first term is a minus 4m squared, and my second term is a minus p. Alright, so that is how we would factor that one there. Now this is our last example in this section, and I'm again going to group these terms how they are written here. So like this. Now our first pair shares a common factor of 5x squared. So I'm going to pull that out. Doing so, I'm going to be left with, my first term is just going to be an x, and my second term is going to be a 3y squared. Now for my second pair here, they share a common factor of minus 5y. So I'm going to pull out a minus 5y, and I'm going to be left with just a positive x for my first term here, pulling out this minus 5y, and then for my second term, this is going to be a positive since we're pulling out a negative, and then 3y squared. So again, we see that both of the resulting terms share a common factor of x plus 3y squared, so we're going to pull that guy out. Doing so, pulling that out from both of these terms, for our first term we're just left with the 5x squared, and for our second term we're just left with the 5y. So this would be how we factor this guy here. Alright, so this brings us to section 5.2, where we're going to be factoring some trinomials, some more complicated than others. Let's start with question 7 here. We have this trinomial in standard form, so it's of this form here. Now in this case, our coefficient a is going to be 1. This is just the coefficient of our x squared term. Our coefficient b is going to be 8, and then c is going to be 15 in this case. Now, whenever we're factoring trinomials of this form, we're going to end up with two factored binomials that look like this here. Now, p and q are just going to be arbitrary numbers such that when we add them together, they're going to be equal to b, which in this case is 8. And then when we multiply them, they're going to be equal to c, which in this case is going to be 15. So what we want to do is find numbers p and q that'll make this true. So the first that come to mind is 3 plus 5. If we let p be 3 and q be 5, we're going to get p plus q is equal to 8, and p times q, 3 times 5, gives us 15. So what we can do is plug those numbers into our factored binomial forms here. So we're going to have x plus 3, and then x plus 5. And what we can do when we are factoring these guys is we can always check them by using our FOIL method here. When we FOIL these guys, we should end up with our original polynomial that we were working with. And when we do this, we'll see that that is the case. We're going to get x squared plus 8x plus 15. So that tells us that this is our factored form of our original trinomial. Let's look at another example similar to the last one here. In this case, a is going to be 1, b is equal to 7, and c is going to be equal to minus 30. So we want to find numbers p and q that'll add together to be b, or 7 in this case, and multiply together to give us minus 30. Now, two numbers that come to mind are going to be 10 and minus 3. 10 plus negative 3 is going to give us a positive 7, but 10 times negative 3 gives us a negative 30. So what we're going to do is plug those numbers into our factored binomial form, which is always going to look like this, in this case here. So we're going to have a y plus 10 and then a y minus 3 here. And again, what we can do is FOIL these guys out here to make sure we end up with our original trinomial, and we actually will in this case, so this will be our fully factored form. Now this next example is a little more complicated, but what we're going to do first is just rewrite this trinomial like this here. Now in this case, if we just pay attention, we look at our variable a. Doing so, we'll see that this is actually in our standard form here. Now our standard form, if we're looking at our variable a, we're going to have some coefficient, in this case 1, in front of our a squared term. So that'll just be an imaginary 1 there. Then we're going to have another coefficient in front of our a term, just like how we have a coefficient in front of our x term here. That coefficient is going to be minus 2b. And then our last term is going to be this c here, and so that'll be this whole thing here, this minus 35b squared. Now, applying this reasoning here using our standard form, and actually, sorry, there should be an a in front of this square term, we can label the coefficients of this guy here. So the coefficient a is going to be the coefficient of our squared term, so that'll be 1. b is going to be the coefficient of our a term, so that'll be minus 2b. And then c is going to be our last term here. Now I know it might be confusing with all our a, b's, and c's here, but this is just to emphasize this is our standard form, and we're just identifying the coefficients of this guy here in front of our squared and our a terms and then our last term. So since we're thinking of this in terms of our variable a here, this means our fully factored binomials here are going to be a plus or minus our p times a plus or minus our q here, where our p times q is going to give us our b coefficient, or our minus 2b, and then p plus q is going to give us our c term, or our minus 35b squared. So here we kind of need to do some guessing and checking to find terms that'll make this true. So first of all, if I let p be equal to 5b and then q be equal to minus 7b, if I were to add these guys together, plus a minus 7b, this would give me a minus 2b. And then if I were to multiply these guys together here, this would give us, multiplying 5 and 7, minus 35, and then b times b is b squared. So this means these are going to be our values for p and q here. So we'll plug these guys into our fully factored binomial form here. So just plugging our p and q values into this guy. We know we're going to have a plus our p value, which would be 5b, times a plus our q value, and our q value is a minus 7b, so we're going to have that there. Now again, what we can do is FOIL these guys out. Doing so, we can see that we're going to end up with our original trinomial. So if we were to FOIL these, we would multiply these guys, these, and these guys here. We would end up with a squared minus 7ab plus 5ab minus 35b squared, which finally gives us our original trinomial that we were working with. So this tells us that this is going to be our fully factored form here. All right, so for this next example, the first thing I'm going to do is pull out a negative sign. And the reason being is because this first term here has a minus coefficient and it's just easier to work with. You don't necessarily have to make this your first step. It'll just kind of make our lives a little bit easier. So doing so, I'm going to be left with this trinomial here. Just pulling out this minus sign, it's going to change the sign of our other terms. So next, I'm going to identify the coefficients of each term here. So the coefficient of our squared term is 6, our m term is going to be 13, and our last term here, c, is going to be minus 15. Now, this is the first example we've seen where our a, our coefficient of our squared term, is not 1. So in this case, it's going to be a little bit more complicated. Now usually if this coefficient here is 1, we know our fully factored binomials are going to be like this here. And what we've been doing so far is trying to find these p and q values. Now the reason why our factored form is going to be like this is because when we FOIL out, our first term is automatically going to give us this m squared. But we can't set it up in this case because when we FOIL these out, our first term needs to give us a 6m squared. So what we're going to do is rewrite this guy, giving us a 6 for this first term here. And then in this example here, we still have this minus out on the outside. So I'm just going to carry that with us as we go through. So in this case, when we FOIL this out here, so multiplying all of these terms, notice we're going to get a 6m squared, which was exactly what we were looking for, but this 6m is also going to multiply this q, this p to this m, and so we're not exactly sure what's going to happen when we add these p and q values yet. The only thing we know for sure is at the very end we are going to multiply these p and q values. So our p and q, when we multiply them, it is still going to give us our last term in our polynomial. So multiplying these guys, we still need to get a minus 15. We're not sure if adding them is going to give us a 13 yet because of this extra coefficient, but we know that this still has to be true here. And it'll be a minus 15 in this case. Now, this method is called the FOIL method, and it's one of two methods that we'll use when this coefficient here is not 1. Now, this method does require a good amount of guessing and checking. So first of all, I'm going to guess two numbers p and q that'll give us a minus 13. And so that would be 3 and negative 5, and this will give us a minus 15 here. So what we're going to do is just plug these numbers into this guy here, and FOIL it out and see if we end up with our original polynomial. So doing so, we're going to have this 6m here, and we're going to add our p value of 3. And then we have m plus our q value, which is going to be minus 5. So from here, we just want to FOIL this and make sure that this is going to be our factored form. So we'll multiply these guys, these two, and these here. So doing that, we still have this minus on the outside. We're going to have 6m squared as our first term. Then we're going to have minus 30m plus 3m and then minus 15. So automatically we can see if we have minus 30m plus 3m, this is going to give us a minus 27m, and that's not what we're looking for. We're looking for these guys to add up to give us a 13m. So that's where the guessing and checking comes in. This is not what we're looking for here. So the first thing we can do when we end up with a situation like this is maybe switch these p and q values. So that's exactly what we're going to do here. We're going to switch these p and q values. So let's see what happens if we have 6m minus 5 and then m plus 3. Foiling this, we're going to end up with 6m squared plus 18m minus 5m minus 15. And then we can see that this ends up being the trinomial that we started with. We get that positive 13m in the middle here, and then we still have that minus 15 on the outside. So this would be our final answer here. And like I said, this is called the FOIL method, and it does require a lot of guessing and checking as we saw, and it's very similar to example 6 in our textbook if you want to take a look at that. And then we'll actually look at another example using a different method in a few examples here. Now, this question here is a perfect example of why it's always a good idea to first try to factor these polynomials by pulling out a greatest common factor. This expression might seem complicating at first. We have a cubed and a squared term, but we'll see that by pulling out the greatest common factor, it actually makes the resulting polynomial an easily factorable expression. So notice that each term shares a factor of a and a factor of 6. So we're going to pull that guy out. The resulting terms on the inside, we're going to have a squared plus 2a minus 15. So from here, all we need to do is then factor the polynomial on the inside of these parentheses here. So this 6a is going to stay on the outside. And we know that we're going to be left with two binomials that look like this here. We're going to have a as our first term. As we've seen in the last examples, we just want to figure out what these numbers are going to be. We've been calling them p and q. We know that p plus q needs to give us our coefficient for this term, so 2. And then p times q needs to give us our c term, so minus 15. So two numbers that would give us this would be plus 5 and minus 3. And then we can FOIL these guys to make sure that we will end up with our original trinomial. And we do, in fact, so this tells us that this is going to be our fully factored form of this guy. So for this next question here, we're going to be using our substitution method to factor this guy. Now we like to use substitution when we're dealing with these more complicated polynomial expressions, and substitution allows us to write these guys in a simpler way. So we're going to start out by noticing we have this m plus p squared and then this m plus p terms here. So by using substitution, we can introduce another variable, say x, and let's let x be equal to m plus p. Doing this, we can rewrite our original expression as 3x squared minus 7x minus 20. Because we said x is going to be equal to this m plus p term here, so we're just plugging x in wherever we see an m plus p. Now, from here, it'll be a little bit easier to factor this guy. Notice that we do have a trinomial in standard form, so we can identify the coefficients of each term here. So notice that the coefficient for our squared term here, a, is not 1. And we saw a few examples ago that we can factor this guy using the FOIL method. But in this case, what we're going to do is try a new method called factoring by grouping method when a is not equal to 1. So to do this method, the first thing we need to do is identify some things. First, we want to figure out what a times c is. So a times c is going to be 3 times minus 20. So this will give us a minus 60. We also want to keep an eye on what b is, and b is minus 7. Now the reason being is in this method, so far we've been using the letters p plus q to figure out what our unknown numbers are when we end up with our final binomial form. So I'm going to stick with that. Using this method, our p plus q values is going to give us our b value, again, this minus 7, but in this case, our p times q is going to give us our minus 60, or our a times c value. Now, I just wanted to point out that this process is similar to what we've seen so far when we're dealing with trinomials whose coefficient is 1 here. We want these p plus q terms to add up to be this b value, and p times q will usually give us our c value. But we need to be careful in recognizing the form that we have when we FOIL our factored binomials. So for example, this is the case here when our coefficient would be 1. When we multiply these guys, that's not going to affect the coefficient value of this x times q term here. However, when we have this case, when this coefficient a is not 1, this guy is coming along for the ride. This a here is going to multiply both of these terms. So that's why we need to incorporate it using this product here. The product of a and c now need to be 60 versus the product, and that's also going to be the same thing as the product of p and q versus this p and q just being this c. Okay, so I hope that makes sense. We're just taking into consideration this a value here since it's not going to be 1 in this case. Alright, so the next step here is figuring out what the options are for these p and q values. So I'm going to let p be equal to minus 12 and then q be equal to 5. Doing this, we are going to get a minus 7 here, and multiplying these guys, we will also get a minus 60. So these p and q values will work here. And so what we're going to do with these values is actually rewrite our polynomial. So what we're going to do is we're going to rewrite this middle bx term here using our p and q values. So we have this we just have this 3x squared here, and we have minus 7x. So what we're going to do is rewrite minus 7x using a minus 12x and a positive 5x. And we still have this minus 20 here. So the whole idea is to break up this middle term, this minus 7x, into two different terms here so that we can then use our factoring by grouping method. So now that we have 4 terms, we can group these guys into 2 different pairs that share common factors. So first off, we're going to group our 3x squared and our minus 12x, and then our 5x and our minus 20. So these guys share a common factor of 3x, so I'm going to pull that guy out. I'm going to be left with x minus 4 here, and then this pair shares a common factor of 5. So I'll pull that guy out, and I'm again left with x minus 4. And now both of these terms share a common factor of x minus 4, so we can pull that guy out. Doing so, we're going to be left with a 3x and a plus 5. So this would be our fully factored form here using our factoring by grouping method. And this example here is going to be similar to, let's see, example 5 in our textbook. If you want to take a look at that. And this is our factoring by grouping method, when our coefficient here is not going to be 1. So this brings us to our last example for this video, and this is again going to be a factoring using our substitution method. So we're going to rewrite this kind of complicated polynomial expression here. Notice if we have 2x to the 4th, this can be rewritten as 2x squared squared. So that'll be our first term there. So from here, what we can observe is that if we introduce a new variable, let's say t, and set t equal to x squared, we can plug this variable directly into this expression wherever we see an x squared. So we're going to have 2t squared minus 9t minus 18. So again, just plugging in t wherever we see an x squared here. Now from here, we do end up with a less complicated polynomial expression here. But notice we still have our a coefficient, or the coefficient for our squared term, is not equal to 1. So we are going to have to do one of our 2 methods that we've seen so far to factor this guy. And so for this one, we're going to continue with our factoring by grouping method. A times c is going to give us a minus 36, and we know b is equal to negative 9. So that means we need 2 numbers that will multiply to be negative 36 and add to be negative 9. So those 2 numbers would be minus 12 and 3. This gives us a negative 36, and then minus 12 plus 3 will give us a negative 9. So what we can do here is break up this middle term into 2 different terms using those values. So we'll have 2t squared minus 9t, and minus 9t can be rewritten using minus 12t and plus 3t. And then we still have this minus 18 here. Okay, so just rewriting this minus 9t using these 2 terms here. Now from here, we can factor this using our grouping method. We are going to group these 2 pairs and these pairs here. Now these guys share a common factor of 2t, so we'll pull that out. What we're going to be left with is t minus 6, and then these guys share a common factor of 3. So pulling that out, we're going to be left with, again, t minus 6, So we're going to pull that t minus 6 to the front. And what we're left with is 2t.
So this will be our final answer here using our factoring by grouping method.